Definitely got the right answer, so I probably have to do it. I found out as I was training in my finance exam that I'm allowed to turn it in. As I was turning it, if they take off 20 times, I might ask why to see. Dude, I am so against telling kids. Look, my logic is that I was grateful if somebody took it over and I failed. So I do think that I think for shit handling.
All right, can everyone hear me? Am I clearly audible? All right, so this prelim has a lot more material than I was expecting as I was making these slides last night. So I guess we can just get started, get right into it. Welcome to the Prelim 1 review session for CS4820. Your prelim, I hope you know, is on Tuesday. And so that's why you're here, to review and to study. Just to put everyone at ease a little bit, you know, the problem sets in this course take so much time that you don't need to study quite as much for this exam as you might think. So, you know, if you haven't gone to lecture for some of your other courses and you feel like you have to cram the whole weekend before the prelim to study, that's one thing. But if you're doing the problem sets, you're actually putting in the work, you're going to office hours, you're trying to come up with correct solutions to these problems, the material does stick quite well. So I hope that you guys aren't too freaked out about what we're going to be doing today. So just a brief survey of the topics that we've covered so far. Very first couple days of class, we talked about stable matchings and Gale-Shapley's algorithm to kind of introduce us to this idea of analysis of algorithms. And then we covered greedy algorithms quite extensively, along with some famous algorithms for computing minimum spanning trees on graphs. Then we moved on to dynamic programming, which is probably the scariest topic for a lot of people in this course. It was for me. And then finally, we talked about divide and conquer and randomization. And the lectures basically stop for the prelim, I want to say on the 26th. So whenever you finished talking about median finding, that's pretty much where this lectures series is going to stop. Actually, no, that's incorrect. Closest pair points is the last thing that you really need to know. And some of the more interesting stuff that you guys have been doing with hash maps and randomization are not going to be covered in much depth on Prelim 1. Next slide. Okay, so who can tell me what the stable matching problem is in some amount of formalism? No one. So everyone's going to get a 0 on this prelim, right? No, someone knows what the stable matching problem is. James?
You're matching men and women. Each of them have a preference.
Right. So Gale-Shapley, they were a little misogynistic and outdated. They matched men to women, and we like to match residents to hospitals. But unfortunately, our slides are kind of old too, so we actually go with the men and women matching problem. So consider a set M of n men and a set W of n women. And each of them has a preference list ranking all of the candidates of the opposite gender. So every man has a preference list of the women, and all the women have a preference list of the men. And now we want to find some stable matching S between the man and the woman. What is a matching more generally? Someone just shouted out, matching. What does that mean? Yeah. Right, set of pairs of men to women, right? And what is a stable matching? What are the conditions for matching to be stable? Yeah.
There's no instability, and an instability is a situation where I guess a man prefers another woman to the one he's clearly matched to.
Yeah.
And the woman that man is clearly matched to also prefers another man to her.
Right. So no instabilities. Is there another condition for a stable matching? Yeah. It needs to be perfect. Awesome. So right, a matching is stable if it's perfect and there is no instability. Keep flipping to the end, right? Back one. And so perfect means what? Perfect means that every man is matched and every woman is matched. So when we have n men and n women, we want no unmatched men and no unmatched women, or no unmatched hospitals and no unmatched residents. Okay, so here's a practice problem. Take a look. We have the men in blue and, oh no, I'm sorry. Basically on the left, we have a table of the proposers and who they're currently matched to. And then on the right, we have another table of the respondents and who they're currently matched to. So can you guys tell me whether or not this matching is stable? I'm getting lots of thumbs down. All right, so why isn't this matching stable? In somewhat precise terms, can someone tell me why it's unstable? Right, we have W2 and M1, and they form an instability with respect to M. And so therefore this matching isn't stable because it violates one of our two key conditions. And note, what I love about that answer is that he said W2 and M1, right, is the unstable pair. So the unstable pair is not the elements of your sets that are currently matched to something else. It's the ones that could break their current matching to then form a new one. That's what we define as our unstable or our blocking pair. All right, does that make sense? Cool. All right, so Gale-Shapley's algorithm will always find us a stable matching. We proved this in class. And the algorithm goes as follows. Basically, every man starts off free, and they're going to propose to every woman one at a time in the order of their preference list. The women are going to wait for a proposal, and if they're unmatched, they're going to take the first one that they get. And if the woman gets another proposal, then they're going to compare the ranking of their current partner to the new person that's proposing to them. And if they prefer their current partner, they're going to reject the new incoming proposal. And if they prefer the new proposer to their current partner, they're going to break up with their current engagement and go with the new proposer instead. Very romantic. And so we keep running this algorithm as long as there's a man who is free and hasn't proposed to every single woman. So first of all, what's the time complexity of this algorithm? N squared. Why is it N squared?
In the worst case scenario, a man proposes to at most n women and we iterate to n women.
Right. So in the worst case, every man can propose to every woman. And when you write this out in code, that results in a while loop of having n squared iterations, right? Which means in order to get this to a truly n squared time algorithm, you have to actually make sure that all of the checking that you're doing between the ranks of various proposers and respondents is indeed constant time. That way you can get the overall algorithm to run n squared. Now, should we ask that question too? Yeah, so is it possible that there are still unmatched men or women when the algorithm finishes? Right, why not?
Because we iterate until.
Right, so we go until all the men are no longer free, right? And if there's a one-to-one mapping between men and women, i.e. there are n men and n women, then obviously no one's going to be free. So some properties of Gale-Shapley's algorithm that you should always be aware of. It always returns a perfect stable matching. And in fact, if the same people are proposing, it always returns the same stable matching regardless of the order in which you do the proposals. Right? So given the same input to this problem, you will always get the exact same unique stable matching in return. And we proved in class that the proposers are always matched to their best valid match, where a valid match is one that doesn't cause an instability. And the respondents are always matched to their worst valid match. So in other words, this is a proposer optimal algorithm and a respondent pessimal algorithm. But note that you can flip who the proposer and the respondent is in your algorithm and still get another stable matching just from a different perspective, right? So what this algorithm shows is that there is a way to find a specific, unique, perfect stable matching, but we could always find another one, or we could potentially find another one, given some permutations of our preference lists and switching the order of the respondents and the proposers. Okay, so now we got some true-false questions. I'm gonna give you 2 or 3 minutes to just read through all of them, make your guesses as to which ones are true and which ones are false, and we'll go through them one by one when you guys are done. Feel free to talk amongst yourselves as well.
Yeah, exactly.
The second to last one.
Yes. Yeah, exactly.
Imagine everybody except for one dude has this woman that was get proposed to by literally so, and then she is not matched.
Yeah, you can just get back to it.
Yeah, I don't know that's true, but I that means nothing about what actually matters for priorities. Because I think
How many people are still thinking through it? All right, we'll give it maybe another minute.
it's the exact opposite. No, that's the last one definitely.
All right, let's go through all of these true false questions. So hopefully if you did the practice prelim, you recognize all of these or most of them or some of them at least. So yeah, let's go through one by one. Who can give me an answer for the first bullet point? The output of the stable matching problem when men propose to women is the same as when women propose to men. Is that true or false? False, right? Because we just described how if you switch the order, you could get a different stable matching. Awesome. Second one, consider an instance of the stable matching problem in which the first choices of all men are distinct. Let these top choices define a matching M. Gill-Shapley will necessarily return this matching on all instances with this property. Right, because we're assuming that men are proposing, right? So if that's the case, then every single one of them will just propose once and get their first top choice. And so it doesn't matter in which order these men propose, they'll have distinct choices anyways. Awesome. Number 3, switch it so that if you have an instance of the stable matching problem in which the first choices of the women are all distinct, let these top choices define some matching. Gill-Shapley will necessarily return this instance. Is that true or false? False, because of what assumption that we made in the problem? Right, because the men are proposing, right? So the women get their pessimal choices. It doesn't matter if their first choices are, distinct, right? They might not necessarily get them. If a woman receives, that's a typo. If a woman W receives proposals from at least K plus 1 men, then she is not matched to one of her K lowest priority men. True or false? Why?
Because when a man proposed, the woman can only improve her.
Right. Exactly. That's also an important property to understand about the Gill-Shapley's algorithm. From the moment when a woman first receives a proposal, every proposal after that she receives can only improve her preference ranking, right? So she's not ever going to take a sequential proposal if she's already matched with a man from someone who is lower ranked than the current partner that she has. And then conversely, if a woman is not matched to one of her K lowest priority men, then she must have already received proposals from at least K plus 1 men. False, right? Does not hold. Again, can someone give an example why?
First person who proposes can be the number 1.
Exactly, right? They could get really lucky right off the bat, right? Okay. Next. So yeah, false, true, false, true, false. So these are kind of like the things you could expect to be asked on an exam about Gil-Shapley's algorithm. It's usually not going to be very interesting to us to ask you to regurgitate the algorithm for some stable matching problem. We're going to want you to think critically about what the algorithm does and some of the things that you've proven in the course. All right, now Emerald is going to talk a little bit about greedy algorithms. Oh yeah, do you have a question? Is like given a preference list, are you? Yes. Yes. Right, because of Gil-Shapley's algorithm. Yeah. Right, it'll always find one given a valid preference list. If you give it some invalid preference list, maybe not. But the cases in which you wouldn't necessarily be guaranteed to find like a perfect stable matching, or if you introduce this notion of like forbidden pairs, or we introduce extra constraints on our problem, then you might not necessarily have a perfect stable matching. But in its raw form, you were always guaranteed to at least have one. Yeah. Okay.
Everyone good? Oh wait. Everyone good? No more questions? Cool. Greedy algorithm. Okay. So the greedy algorithm we covered so far, we have interval scheduling, interval scheduling to minimize lateness, and minimum spanning tree. Next slide. And these are the proof techniques we should know by now. Greedy stays ahead and exchange arguments. Minimax, it's not required. You can solve basically all greedy algorithm with the other two proofs. So we will not be covering minimax in this recitation. You can review the lecture notes if you need to. Next slide.
Wait, I just want to emphasize that when we say optional, we mean truly optional. You can solve every problem on this exam without it. It's just if there happens to be a case where you think it would be useful, you are more than welcome to use the technique if you understand it well enough. But we gave you like no resources as to how to do that other than some brief notes in the lecture. So, you were not expected to know it, and it shouldn't really be something that you're like stressed about. I don't feel like you have to understand it to define it. It's like really if you've seen it in other courses and it happens to be useful here, you're free to use it.
Okay, let's first review interval scheduling.
Can you use minimax to prove everything that greedy says ahead can? Like in what instances would it be useful to use it?
So I think formally it would be useful when two problems are equal of each other and you can use like minimizing the maximum to formulate maximizing the minimum. Again, I'm saying words that I personally don't really understand that much, and so I don't know if there's like a more comprehensive way to help.
Any more questions? Cool. Let's review some interval scheduling thing. So this is a question. Given a set of n requests, as well as a start time Si and a finish time Fi for any request I, how do we schedule as many requests as possible? And of course, earliest finish time is the greedy rule we're using. Next slide. And I'm just the green ones is our algorithm. And by the way, just to say this again, you're not required to write pseudocode on your solution. It's if it helps you to think about a problem, you're more than welcome to write it. But we actually prefer if you just explain your algo in English. So for this algorithm, you start by first sorting all the requests in increasing finishing time, and initialize like a set of A, which will be the request that you take. So while R is not empty, you choose the next request I according to the sorted order, and you add that I to A, and then you delete all the requests that have a conflict which you cannot take, and finish that while loop. We have our answer. And for the runtime analyze, the sorting part is NLN, and you can see that we only run through every request once. So the running through the array will be ON. So altogether, the overall runtime is N log N. And why does this algorithm work? We'll prove this later, but the intuitive explanation is that like you want to take the earliest finishing time request first, so you have more like possibilities for future requests. Next slide. And how do we prove this thing? What are we trying to prove for this problems? The size of the output set for our greedy algorithm is equal to the size of a optimal set of intervals. And for this one, we can use greedy stays ahead. And we use induction to prove this. And this is the proof. So first, what does it mean for our greedy algorithm to stay ahead? You need to define what is staying ahead, right? So say, let I, k, j, k be the kth interval in the greedy algorithm set, and any optimal set of request. And we want to show that for any finishing time ik, for all k, any fi will be smaller or equal to fj. That means it finished first. The request finished first. And I will not go through the whole proof, but if you're interested, it's on 122 on the textbook. Any question for this question? Next slide. And here's some tips for the greedy algorithms. Just like because we learn both DP and greedy, and like many of you sometimes have questions like, which one do we choose? Do we use greedy? Do we use DP? So the general idea is that you maybe, like if you have no idea which one you should use, maybe start with the greedy and try to come up with a counterexample. If it doesn't work, then you switch to DP. Yeah. Uh-huh.
So, can you just say again what it means, what we're wanting to show that F5K is less than for the FJK?
You mean what does want to show that thing means? It means for every, so like k is the kth interval in the set of requests that we are approving, right? We're picking, and ik is like our algorithm, and jk will be in the optimal or any results. So this part is saying that our request on that index finished first. So by like, if you can see, it shows that we would potentially have more requests in the same intervals. Does that answer your question? Okay.
We start by just saying that, like the first one we choose is like definitely less than or equal to the first one.
Yes, that's the base case, and you induct after that. Awesome. Any more question?
So for DP and greedy, can we just like use DP if they just say it's a point of, we need to get a point of time algorithm? Will we get penalized? It's actually a greedy algorithm, like a greedy algorithm.
If you find it easier, you're more than happy to use DP. But I would find that hella.
Yeah, it's okay to use DP for greedy. I personally accidentally used DP to solve a DC question last year. But it's okay. Yeah, you can use DP. As long as it's correct.
Is that in the prelims question, if we cannot come up with an algorithm calculus to get it done, that would have some point rather than not have an algorithm at all? That we
It's exponential time, you probably won't get too many points. You might get a point for some merit, but exponential time, I would much rather see a well thought out, but maybe slightly incorrect solution. I guess using the techniques we learned in class rather than giving an exponential time recursive algorithm.
Just real quick, there's like another part for the stays ahead group, right? There's like a little bit that to me to show like why you don't use the greedy rule for something in a proof, another proof, right? Or something. Can we just say why greedy stays ahead?
You mean how do we prove greedy stays ahead?
I don't know how to prove greedy stays ahead. But we have proved our greedy or inductive. We have to do the proof after.
I think that's in our next slide.
Okay.
Should be.
So finishing this part, if you want to see more proofs examples, here's some suggestions. And you don't have to use reduction, but if you want to, like say interval scheduling, you find a really similar question, you can use induction. You are allowed to use induction. Next slide. So this is I guess the whole process of how to prove greedy sits ahead. So first part you define what is staying ahead, and actually first step you define your solutions. That's just for your notation, right? Like A is our solution and optimal is O. And second part you define like what is staying ahead. Third part is the actual proof, the induction part. You have base case, the inductive step, and after all that, you kind of prove the things already, but we want to use like another summarization to show how by proving this, why do we have the proof for the actual problems. So an example is just say your output A in interval scheduling contains same amount of requests as the any optimal step. Therefore, our solution is as optimal. Just want to like make a conclusion. Does that answer the question?
Yeah, but you cannot just say that like, oh, from the inductive hypothesis that we just proved, our algorithm is correct. You must like finish the proof, right? There is some step of logic that goes from proving that the finish time of each interval comes before the finish time of any other interval scheduling algorithm output, and why that then implies the optimality of the algorithm that we've constructed, right? Those are not necessarily the same thing. So you do have to like, usually like a proof by contradiction or something really short to like finish it up.
Yeah. And here's a good greedy stays ahead example from the textbook. Okay, I will not go through this right now since we are like we have a lot to cover. Oh, okay. We can just work on this question now. So if you have any other question about the Prelim, like you can raise your hand. I'll come on right now.
Is anyone confused about like what the problem says? Same one as your recitation. Yeah.
Oh, you have to say that. Oh, okay.
Next one.
So like,
If you did, it's fun. It's always good to like problems, right? One that's simpler and can be solved.
you're
It's the same way.
That is. Oh, we're not. We giving you the offer. That is not an offer.
Okay, it actually determines the number of shots. So I probably
Oh, I just remember second. I was saying like companies.
Yes.
Oh, I see what you mean.
sometimes sending off a truck.
That is the sorry. That like you're trying to put that company policy. Any other algorithm like doesn't have to satisfy.
Solution is one of the ones that will always shift, should always be. Oh my god. What do you mean? Like, it's always gonna be. Oh, I was gonna
You're
say,
saying that
the total weight of all functions for this green algorithm is always greater than that for the option. Or, that's, I mean, like any other arbitrary something. Because like. Yeah, that makes sense.
well, the algorithm is already given.
Any questions?
Yeah, yeah.
You guys got it?
I'm rolling.
There are other.
Yeah, that's what I'm saying. So the first thing what do you think is the
I think it was.
Like you have a sum of weights on a truck.
Actually, before ask anyone.
Yeah, it has to be.
Ask if anyone knows. No, sorry.
I mean, I think you actually. I don't think we can necessarily say it would be always one because they could take on.
Okay. Can I get a raise back off the hand? How many people still working on the question? All right. Seems everyone's good. Cool. So can anyone tell me what when you're trying to prove this, what is staying ahead? What do we want to prove is that's staying ahead?
I want to prove that our greedy algorithm is staying ahead compared.
But like, is it time? Is it weight? What are we staying ahead? Definitely not timing this one.
Time is fixed. It has to arrive in the order that they're talking.
Yes.
Number of boxes.
Yes. The number of boxes is the greedy rule that we're trying to stay ahead for this one. Next slide. So, this is our proof. First we denote our notation. Say let A be the number of trucks our greedy solution uses. Actually, the answer that the other student just proposed was correct. We could induct on given the number of trucks, how many boxes we have. This is just another solution. It inducts on the number of trucks our greedy solution uses. It's basically the same thing, the same idea. So we denote our notation, and it defines the greedy solution, so you had say for the first K trucks, let our greedy solution packs these boxes, and for any optimal solution, we pack B1 to Bn boxes. And we want to show that in our final result is to show that M must be larger or equal to N. That means given the same amount of trucks, the boxes, we have our algorithm have more boxes. And this is the induction part. I'll just give you guys a minute to look at this question.
Confused about what the optimal solution. So we're assuming the optimal solution is ordered in the same way.
You define it.
Yeah.
The-
You need to ship them out in the order that you get them, right? So like getting like a stream of boxes, box 1, box 2, box 3, all the way to box whatever, right? And you have to like what you decide is which truck you put it in, right? So like if I put in box 1, I can put it on the first truck, right? Or maybe in the optimal solution, I'll wait 1 truck.
Yeah. So
So you have to still ship them out in the same order.
You can say like say
that's the primary answer. I thought it was like I thought the question was okay.
any other question? Okay. And you prove the via induction, and you just say in conclusion, the total number of trucks smaller, so we have our algorithm as optimal. Any other questions? Okay, next slide. And here is the other proof that we should know is exchange arguments. Also 4 steps. First step is to define, same as previous ahead. We want to define, say like A is our algorithm and O is optimal. And second step, we assume that our greedy solution and the optimal solution or any solution is different in some way. It could be the elements are different, it could be the order is different, but they're different in some way. And we want to show in induction part, I mean sorry, not induction part, in the exchange part, that by making the optimal solution closer and closer, more similar to our algorithm, the optimal solution remains their optimality. That shows that our algorithm is better and therefore optimal. And just to elaborate again, that we are swapping O into A, not the other way around. We should all know this by now. And after finishing that, we have a conclusion. You just say, because we did that, just this whole thing here, right here. Do you have any question on this proof strategy? Okay, next slide. I'll give this back to Evan.
All
to
right.
minimum spanning tree.
All right, so now we're going to talk about minimum spanning trees, and I didn't mention this so much earlier, but really up until Prelim 1, you guys have learned like 4 different famous algorithms, right? The ones that have names of old white people associated with them. So the first one was Gale-Shapley's algorithm, and you should be able to run this on an exam. And the same goes for Kruskal's algorithm, Prim's algorithm, and Bellman-Ford's algorithm. So all these algorithms are ones that like you should honestly have committed to memory, right? Some of the other algorithms in class you should definitely understand. You should definitely be able to use them in good ways, but we probably won't ask you to run interval scheduling on an exam, right? Like given a valid input to interval scheduling, running that algorithm is not very interesting, so we're not going to ask you to do it. So with that, let's talk about what the minimum spanning tree problem is. So it's an incredibly important topic just in computer science in general. Given an undirected graph G, which we can denote as a set of vertices and a set of edges, we call them V and E, with costs on each edge, so it's weighted, find a subset of the edges T such that the graph V comma T is totally connected and the total cost of the edges in T is as small as possible, right? So we basically want to choose a subset of the edges that make sure that our graph still remains connected as one whole connected component, but the cost of all of the edges that we're taking is minimized. Right. So why is it that the output is going to be a tree? Right? Why is it not going to be like just a graph more generally? Why can't I say it's a minimum spanning tree? This is a little bit of a what's that called? Foreshadowing for some of the other slides. Go ahead.
Any connection that would add a cycle would be an unnecessary expense.
Right. We're adding now another edge that would then take us to the same nodes that we've already covered, which we don't need to do. All right, so we learned two famous algorithms for constructing minimum spanning trees, and we learned how to prove their correctness as well. So Kruskal's algorithm is simple. We start by just sorting all of the edges in ascending order of cost, and we add each edge to our minimum spanning tree so long as that edge does not introduce a cycle in our graph. And what's the runtime of the algorithm? Just shout it out, it's on the screen too. No one wants to talk. Damn. Right? M log n or E log v. And we can do this how? You guys had to implement this. What data structure do we have to use to get it down to E log v? Union find, right? So it's not that trivial to get this down to E log v, but it can be made E log v in the amortized case when we use a fancy data structure like union find. We're not going to quiz you on the details of union find, although you should know it because you implemented it. But that's how you get the runtime down to E log v. The second algorithm that we looked at is Prim's algorithm, which has the same runtime very conveniently. And we start by just saying, let me take any arbitrary node in my graph and let that be a connected component. And then I always choose the cheapest edge that extends from that connected component into the rest of the graph. And I keep doing this until I've connected every single node in the graph. And this will return the minimum spanning tree of cheapest cost, right? And so one of the key things here is that it doesn't matter what node we start from. Why does it not matter what node we start from? Because we need to connect all of them anyways, right? Like we're going to end up covering every single node with our minimum spanning tree. Therefore, it makes no difference which node we start building the minimum spanning tree from, as long as we follow this greedy rule. And we can get this down to E log v time using a heap-based priority queue, but you did not implement this algorithm, so if the details of that are fuzzy, it's perfectly fine. So the key ideas for the proof are two fundamental properties that you should be able to recall on the exam. The first one is a cut property. So we define a cut as being some partition of V such that basically we have all of the edges that go from S being the first side of that partition and V minus S being the second side of that partition. And all of the edges that cross the cut we define basically as being in the cut, right? And we say that the cheapest edge that crosses the cut from S into V minus S is in our minimum spanning tree. And not only is it in our minimum spanning tree, it is in every possible minimum spanning tree of any execution of any minimum spanning tree algorithm. Right? So that's a very fundamental statement. And the way we prove that is by using the exchange argument that Emerald talked about, where we assume the optimality of basically some other solution, we make it look more like our greedy solution, and then we can prove that this property holds, right? And we use the cut property in the proofs of optimality for both Kruskal's and Prim's algorithms as well. V is our set of nodes. Yeah. So basically we're saying partition our nodes into two sets, one being S and the other being V minus S. Yeah. Yeah, so this is the same thing defined just slightly more precisely. Go on. All right, the cycle property is the second fundamental property of minimum spanning trees that you should be able to recall and use on an exam. And it basically says that assume that all of the edge costs are distinct, and let C be any cycle in our graph G, and let the edge E, call it connected by VW, some nodes, right, be the most expensive edge in our cycle. That edge cannot belong to any minimum spanning tree of our graph. So no matter which algorithm we run, however we want to form this minimum spanning tree, I know with absolute certainty that the most expensive edge in the cycle cannot be in the tree. Okay, so here's some practice. Let's go ahead and find the minimum spanning tree of this graph using Kruskal's algorithm. How fun. So what's the first edge that we're going to choose? Also, side note, and a lot of the times when we give you these problems, we say assume that the edge costs are distinct, right? If the edge costs are not distinct, does it really make a difference?
between perturb small genius. So at the end, we have distinct because of the small genius, but it don't matter overall.
Yeah, right. So yeah, we can still find, and in fact, if some of the edge costs are ties, we might find multiple minimum spanning trees, right? That's a possibility as well. So, okay, yeah. So what's the first edge we'll choose using Kruskal's algorithm? Yeah, GH or DF, right? And then the next edge that we'll choose, probably the other one, right? Then we'll choose BH, right? GE, yeah, so on and so on and so on until you find the minimum spanning tree of our algorithm. And so this is the first solution that connects all of our nodes using Kruskal's algorithm. And again, on an exam, you should be able to fully run and get this output. And then on the next slide, we see a second solution that results in the same cost minimum spanning tree, but because some of the edge costs weren't distinct, we were able to find multiple solutions to the problem. Yeah, that was fine. Similarly, we can use Prim's algorithm, and it looks like in this example, we started with E as our root node, and we just grew outward from the root node until we connected our entire tree, getting something that looks very similar to the minimum spanning tree for Kruskal's number 1. And then we can also do the same thing, making a slightly different choice to get the second output of Prim's. Oh, those are. All right, a practice question. So we have a weighted undirected graph G, and we have a minimum spanning tree for this graph. And suppose we add a new edge to our graph, VW. Let G naught denote this new graph, and let's design an algorithm with O of n running time, so we cannot just rerun Kruskal's or Prim's algorithm, to compute a minimum weight spanning tree T naught of the graph G naught, right? So we need to use the information that we had from our original spanning tree T to design a new spanning tree T naught. So I'll give you guys a few minutes to think about this.
About cycle findings, because I already looked over the question and I didn't know that. How is the cycle finding algorithm actually work? We know there's ON, find the cycle. So it's like,
Also, like, I don't like this cycle finding algorithm like for any graph, like, right? Like you can do that normal. Oh, this is like you're adding a new edge, right? It says you already had a tree, right? On the graph that covers all the yeah, so it would not be too hard to find the cycle since you already know like
that's what I want to know. Like, how do you find it? How does that find that cycle? How do I say in a proof that I found that cycle, that I can find that cycle? How do I say it? Oh, that's not find that cycle.
Go to circle, so you find it.
I can just like say that.
Yeah.
Okay.
Yeah, like all you can do is just literally like, and then when you get back where you are, like enter the
Maybe I'll go back to that.
Anyone have any ideas? Why does it create a cycle?
Because we know that we already have a minimum spanning tree of this graph. We're not adding.
Right. Good. Yeah, that's a great algorithm. Go ahead and move to the next slide. Right. So what happens to T if we just add this new edge VW to it? Yeah. Right. So if we add VW to T, we must have a cycle. Why? Because T was a minimum spanning tree on our graph of cardinality V nodes, right? And that minimum spanning tree had n minus 1 edges to connect to the n nodes. And now we've added another edge, and we already had all of our nodes connected beforehand with the minimum spanning tree. So adding this new edge must induce a cycle somewhere in this graph. And I know where to start looking for that cycle. I just start from that edge, right? Because that edge must cause the cycle. And so now we're just going to go through all of the edges in the new cycle that's formed and remove the maximum cost edge from that cycle. Because by the cycle property, we cannot have that edge in the minimum spanning tree. Therefore, we only want this new edge VW to be in our minimum spanning tree if it strictly decreases the cost of the tree, right? Otherwise, we don't want it at all. Does this make sense? Cool. Anyone confused on this solution or need more elaboration? Yeah. So we already know that like adding the edge VW itself will cause the cycle, right? It will be a part of the cycle. So start from there. Look at all the nodes connected, or look at all the edges connected to that edge. Yeah. Yeah. They're not the same. Yeah, how are they defined? Go back. No, they're not the same. No, right? G naught or G prime has this new edge VW in its set of edges, right? So they've got the same node set V, right? But E is different. It has an additional edge. Right, right. So we're constructing T prime from T, right? Basically, given that we already know what T is, we can find what T prime is. Yeah. Okay, so that takes us to the exciting topic of your first prelim. I will give us a 2-3 minute break first because we've gone through a lot, and then we'll start dynamic programming.
Still gonna go over like the
I was interpreting that wrong way. I thought we were adding another node.
no, have another
At least,
Okay. Because I was thinking
I wrote it down.
one head, there's no way you can do Yeah, I know.
All right, let's get started on the fun stuff, right? Everyone's favorite section, right? Chocolate bars with raisins in them for some reason. Problems that get taken off of your homework because we didn't actually know the correct solution as we were giving it to you, right? It's our favorite part of the course. So, all right, so dynamic programming, right? I think that in this class, dynamic programming gets taught in such a way that makes it really, really intimidating. But all dynamic programming is an optimization of brute force recursion over every single possible answer to your problem, right? That's all it really boils down to. Like if I run the Fibonacci recursive function to calculate a Fibonacci number for some number n, right? I do it by then splitting up my recursive call into n minus 1 and n minus 2, and that has 2 more calls, and that has 2 more calls, et cetera, et cetera. It does an exponential time algorithm. But if I do some fancy things, like I memoize it and I cache solutions to previous subproblems, I can cut the runtime down from exponential to linear, right? And that's all really dynamic programming is. Fundamentally, it's a way for us to cut down exponential runtime solutions to linear solutions or to polynomial solutions if they exist. So key idea, break a problem down into subproblems, and we typically take a constrained version of our original problem and we observe like some smaller input of that problem until we get down to our base cases. And then we're just going to solve those problems starting from the bottom. And we're going to gradually build on the subproblems until we get all the way back up to what we wanted in the first place, right? So the characteristic, we always need a base case for every single DP algorithm. And we always need some kind of recurrence, right? Because these are inherently recursive algorithms, right? We implement them iteratively, but they're inherently recursive algorithms. And then we have some form of memoization, right? We store the subproblems to use later. Whether we're doing it from the bottom or from the top doesn't matter. We still need that component in our DP algorithm. Right, so what's kind of the process that you should be going through whenever you see a DP problem on the exam? First of all, make sure that it's actually DP. Like we were saying earlier, it might be a greedy problem. Now, if you happen to solve a greedy problem using DP, do not be worried. If it's a valid polynomial time solution, you will get full credit. If you happen to solve a DP problem using greedy, be very worried. You're not going to get full credit because it's not a valid solution, right? The point is that dynamic programming algorithms are needed in cases where greedy algorithms are insufficient, right? Greedy algorithms are often much more efficient than dynamic programming algorithms, but we are saying the problem is too complicated for a greedy rule to be able to find all optimal solutions, right? So we need some form of dynamic programming. So in my experience, the best way to think about dynamic programming problems is to just think about none of the optimizations, just think about the problem recursively. Like if I was able to break this down and look through all of the possible solutions of this problem, what are the answers to the subproblems that I need to compute the answer to the next problem? And so that's where we have to precisely define our subproblem. And once we have that precise definition, the rest of this becomes quite easy, right? We can think about what our base cases are, what happens when our table gets all the way down to the beginning or the end, and then we think about the order in which these subproblems are built up. And if you've defined a good recurrence relation and you're doing this top down using recursion rather than iteration, then you don't even really need to consider the order in which these subproblems are built up because your recursive call will do it for you, right? However, if you wanted to do the bottom up version, then you're going to need to think about, okay, in which order do I write my for loops to make sure that this algorithm gets executed properly? And then finally, we need to think about how to get to the original question, right? How do we answer the original intent? And so this is our backtracing that we're going to talk about. And finally, the proof of correctness and runtime, which luckily for DP is much easier than it is for other portions of the course. This is basically everything that I just said, isn't it? But one key idea that you should take away is that if we have a problem that says, give me an optimal schedule or give me an optimal set of items, right? When I'm doing a DP algorithm, I can't construct an algorithm that will just give me that set of items from right off the bat. I might want to find the value of the maximal solution, right? So the set of intervals that gives me the maximum value, or the set of items that gives me the maximum value, or the thing that minimizes my total cost, right? I want to frame it in terms of a numerical problem rather than a selection problem, and then I can backtrace through my DP table to get to the end. So in Bellman-Ford, we didn't say what is the shortest path. We said what is the minimum cost path, right? What is the cost of the shortest path? And then from there, we can backtrace and get our solution.
Just a quick comment about the proof of correctness for DP. I noticed this like while I was grading a proof. So for recurrence, like you have to prove these by induction, right? And what the induction proof is really for is just saying like, oh, I computed my earlier problems correctly, and because my recurrence relation is correct, then I'm proving I'm solving this like current problem correctly, right? You don't need to like go through the details of like your recurrence inside your induction, right? Instead, like maybe like outside of that proof, you should like argue why your recurrence is correct, and then later in your inductive step, you should just cite your recurrence.
Yeah, that's a great point. So that's why you want to precisely define like the subproblem itself, right? What does optiv mean, right? Don't just say optiv is optiv -1 plus some other thing, right? No, I want to know what is optiv in terms of like the current set of solutions that you're looking at. And then once you have a precise definition for that, you can proceed with the rest of the explanation in the proof. Yeah.
So we're not allowed to prove our recurrence is correct and then say that our algorithm is correct because our recurrence is correct?
You have to like after you see your recurrence is correct, right? Like you're filling up this table, or you're doing some kind of recursion, right? And you have to argue by induction or strong inductions, like, oh, I solved my smallest subproblem correctly, right? By the induction hypothesis. And now because my recurrence solution is correct, and because I solved the smaller problem correctly, I'm solving the bigger problem correctly.
Wait, so the recurrence, you have to prove the recurrence separately and then inductively. You have to prove the recurrence inductively.
No, the recurrence is not an inductive proof, right? The recurrence is saying like, oh, like usually it's actually like contradiction, right? It's saying like, oh, like take this other smaller subproblem, right? And if it wasn't optimal, right, then we could make it optimal. That would be.
Oh, okay.
Okay, yeah. So we're looking at different types of subproblems here, right? And one of the first problems that we looked at when we introduced this idea of dynamic programming was the weighted interval scheduling problem. And this is because you conveniently saw the non-weighted interval scheduling problem, which is just an instance of this problem where every single interval has a value of 1, right? So note also that you have DP algorithms, right? They can usually be reduced to solve some greedy version of, an algorithm that we've already seen. And so the original problem was that we want to find the maximum total weight of a non-overlapping subset of our intervals from 1 to n. And so what is our subproblem precisely defined in this case? We say optiv is the maximum total weight of a non-overlapping subset of intervals from 1 to I, or optiv j goes from 1 to j, right? That's the problem that we want to solve. And then we find it efficiently with some recurrence, right? And we write down our recurrence to compute that subproblem. And then once we've defined what the base cases are, right, what is optiv 0, then we can just iteratively compute the rest of the subproblems. And this one was a little bit tricky because we had to define this P of j thing, where P of j was like the rightmost interval that didn't conflict with our current interval j to the left of j, right? And so you are going to need to think about sometimes like, okay, am I just going to be looking at optiv -1? Or if I take this solution, and a lot of DP problems have this kind of structure, do I take this solution or not, right? And if I include this choice in my overall solution, what does that then imply about the other solutions that I'm allowed to contain in the same problem? So that was for a one-dimensional table or a 1D array of opt values that we calculated. But sometimes 1D isn't really enough, and it does not encode enough information about the subproblem in the solution. And so we can then look at problems like knapsack, where we wanted the max total value of a subset of items with total weight less than or equal to big W, chosen from our items 1 to n. And so the subproblem was on I little w, and it's the max total value of a subset of items chosen from items 1 to I, subject to some max weight little w. And this then kind of narrows down the choices we're allowed to make at a local level, but then we have to consider more choices at a global level, right? Also, what is the runtime of the knapsack algorithm? Anyone who wants to venture? Yeah.
N into capital W.
Right. Right. It's pseudo polynomial, right? Knapsack is not a polynomial time algorithm. It's a pseudo polynomial time algorithm. And knapsack also can't actually be solved in polynomial time.
There's no now.
Yeah, there's no. NP complete.
We currently, as computer scientists, do not have a way to solve the knapsack problem in polynomial time because it belongs to a class of problems that is called NP-complete, which you'll learn a lot more about later in this course. But for now, the only thing you really need to take away from this is that knapsack is not polynomial, right? Please do not write the knapsack algorithm on your exam and say, polynomial time solution, we're done. If we ask for a polynomial time solution and you give a reduction to knapsack, you're actually making it not polynomial. And so, yeah, don't make your runtimes worse, right? Make your runtimes better. Yeah, we kind of already went through all these steps, right? Define your base cases. So once I have some sort of base case, then I can kind of construct some sort of recurrence that builds up on those base cases. Yeah, you just keep going. You think this is useful? Okay, so yeah, now we can talk a little bit about the proof of correctness. And like we've been saying, it's a brief proof by induction. Honestly, if they give you a dynamic programming algorithm on the prelim, they will usually say you don't need to prove its correctness. So that might be a little bit of a hint. But they might, right? Don't bank on that, right? Please don't bank on that. But but they might say, right?
Please do how to prove your thing.
But the point of me saying that is that the proof for DP algorithms is usually kind of trivial. Like you don't need to give a super lengthy explanation as long as you've clearly defined your subproblems, defined your recurrences, and explained how to get those things, and from those things, then how to get your optimal solution. You don't need to be writing like a page long or a page and a half long proof by hand as to how this actually works. You can usually do it in a little under a paragraph if you're concise. And so I will also say that we have read many P sets this semester that are maybe not the most concise. We have read lots of 16-page, 30-page solutions to some of these problems, and really, you have 90 minutes, guys. Like you don't have enough time to be writing more than a page for a solution on an exam, particularly if it takes you some time to figure out the algorithm itself, right? You might need to start over in the last 20 minutes of the exam, in which case you need to whip up a quick, brief proof of correctness. So yeah, please do not be unnecessarily verbose. Save yourself the effort, save our poor souls the effort when we're grading. Be concise.
The most important part is your OPT. Make sure your OPT is correct.
Right. Clearly define the subproblems and then clearly define the recurrence. And if you've done those things, you will get like 8 out of 10 points just off the bat. Yeah.
So if on the exam doesn't ask for like the max value of these weighted intervals, but it says to actually give like can you write out a TD algorithm that returns the max value and then just quickly write like now backtracks on intervals, or do you have to like explicitly explain like a backtracking?
You do need to explain your backtracking. You need to give like basically a subroutine within your overall algorithm. Similarly, if you're pre-processing at all, you need to give a subroutine that actually properly pre-processes your algorithm. You can't just say we're going to pre-process to do this, we're going to backtrack to do this.
So like, would you need to give actual pseudocode or
Just give an explanation. Please, explanation of the pseudocode. Like you can say like, oh, we look back like, and you see like, oh, like for the example in the homework, like you see which costs match up, and then we choose that one as the previous one, and we just choose this.
Yeah.
Like you don't have to. It doesn't have to be super explicit. You have to give a whole algorithm of proof. Just explain how you do it.
You can also do it mathematically too, right? You can say if opt of ij is equal to opt of I j minus 1, right? Then choose that solution in our subproblem. Like that's also a perfectly valid way of doing it, and that doesn't require pseudocode per se. Just say trace through our table by looking for these conditions, and that's perfectly fine. Oh, and then the runtime. Sorry, go back. Yeah, and then the runtime analysis. So if you're doing this bottom up, the runtime is usually pretty trivial, right? The one caveat that I would say is make sure you don't forget to include the runtime of your actual recurrence itself. Sometimes it's just a max over 2 items, in which case it's constant, which is great, and you're done. Sometimes it's a max over an interval of things or a list of things, and that's a linear time, basically recurrence, and inside of more for loops that would raise the order of your overall algorithm by another n, right? So make sure that you're careful and you don't fall into any subtle traps when computing your runtimes. It's fairly simple. It's probably the easiest part. Just make sure you finish the problem. Yeah, let's talk about greedy algorithms versus dynamic programming algorithms, right? When do I use each one? So both of them break down your overall solution into a series of decisions that you have to make. One of them always makes the same choice every single time, right? Greedy always does the exact same locally optimal solution at every iteration of the algorithm. DP considers a wider array of choices at each interval of your subproblem and then makes a solution like that. And so dynamic programming really does enumerate all of the possible solutions, right? It doesn't really just choose the locally optimal one. It looks for like continuation of an optimal path through your entire table, which is why we need some kind of recursion, which is why you always see basically like a tree-like structure when describing DP problems. If you've been doing some leak code, you might see it often described that way. If you're unsure of whether a problem is dynamic or greedy, some just general heuristics, right? Like the more constraints on your problem, the more likely that a dynamic programming solution is going to be necessary. So if I'm adding in like not just a maximal set of schedules, but one that also maximizes my value, perhaps I need dynamic programming and not just a greedy solution. But if you're unsure, I would always start with a greedy rule. Try to see if one matches what you're thinking of. And if none of them seem to work, then probably go on to a DP algorithm. But don't spend like 45 minutes trying to come up with a greedy algorithm if you just can't find a rule to work. Because like I said, you can also just solve it using dynamic programming, and it is perfectly valid to do so, as long as it's done within polynomial time.
And also, just another quick note, like, it won't be like some absurd greedy rule that you have to like spend like 20 minutes thinking of. Like, most of these will probably be something that you've seen in the practice prelim or in class or on homework. Like, I mean, usually it will be like that. But yeah, so don't spend too much time trying to make a solution, right? Like if you try like the first few things that you think it might be, and it's not that, just try.
Yeah, and another thing I will note before moving on from this slide is that the difficulty of greedy versus DP kind of go up and down in different ways, right? I will say greedy algorithms are really easy to formulate, right? You just pick a rule and then go by that rule, but they become much more difficult to prove. Because are you actually sure that works? That isn't super intuitive. I'm not sure if that greedy rule is actually going to hold for the entire algorithm. Whereas DP algorithms take a little bit more thought to kind of formulate your recurrence and your base cases and your subproblem. But once you do, the proof follows very naturally from that work. So just kind of a note about that. You could have an entire greedy algorithm question on your exam that does not ask you to come up with a greedy rule, but just asks you to prove it, right? Like we did earlier on the slides, and that in and of itself takes quite a bit of time to do. So we're not going to be, so harsh that we expect you to do a homework's worth of work in a 90-minute prelim, right? Okay, so now we have an example dynamic programming problem that we want all of you guys to try out. I'll give you some time to think through it, and then we'll go through the solution all together. Have fun.
You stop again at minutes. Stop at I stop at minutes. Well, then, before you stop here, it comes down. Stop it, okay, you stop it. And.
Let's have like a mutual recursive like double off function basically. For readability.
How many people are still thinking through this one? Perfectly fine if you are. This one is a bit tricky, so. Questions on the phrasing of the problem? We'll give it a couple more minutes and then we'll go through the solution.
Oh, actually, I
the end, you would.
All right, so let's go through it. This one is a little bamboozling, but that's good. That means we need to practice, right? So can anyone try to like precisely define a subproblem for me with the constraints that we're given?
Subproblems, you're at a specific time and you're deciding whether to switch or to stay.
Yeah, I mean, I guess that's like your local decision, right? When we say subproblem is like we want the optimal solution on like maybe I minutes, right, with maybe some extra constraint, right? Yeah. So yeah, our first idea, right? What if we just say the maximum possible value for a schedule with times from 1 up to I, right? That's what optiv is. But the problem with that is when we try to determine what optiv is, we don't know what machine was run last to give us I minus 1. So we don't actually know if we need to wait to select the ith solution, right? Because we might have to just not do anything at minute I if we're switching from machine B to machine A or machine A to machine B. But we don't know. So chances are this subproblem is not rich enough, right? The second idea, what if we include which machine was run last to give us the schedule of the optimal value? And so we say optimize the max possible value for a schedule from times 1 up to I, where the last machine run was to give that value, and that's stored in a tuple of some kind. So the problem here is that even if we do know which machine was run last to find like some particular value, we don't know if it would have been better to not have used that machine last. So for example, like just keeping track of what was the most recent machine isn't necessarily going to be enough to generalize to this overall schedule that we need, right? So we have some counterexample here, but we need to know that, right, yeah. We need to know if there would have been a better path, basically, right? Would it have been better if I ran machine B at minute I minus 1 instead of machine A? Not just, oh, I did run machine B at I minus 1. Does that make sense? Right. So even this kind of lacks some constraint. One more. So go back. Yeah. So here's the final basically idea, right? We're going to store not one opt table, but 2 opt tables, right? Opt A is going to be the max value for a schedule from times 1 to I, where machine A is used as the last basically machine at time I. And opt B is going to be the optimal schedule from 1 to I, similarly, where machine B is used at time I. Yeah?
Can you just as easily done that with the second idea, but then running it twice, starting with A, and then, or like if you say you use A at time N or B at time N, and then just figure out which one gives the more maximal value?
So you're saying just include all of it in like a single subproblem?
Yeah, I mean, like, isn't your final idea essentially the exact same thing as the second idea, but you're just running it twice?
So, like, the reason why we have to have two tables is because, like, let's say, like, we're trying to compute, like, the maximum value of us, like, ending on computer A, right? We need to consider whether or not, like, we stayed, like, from the previous one, like, we stayed on A, or we switched to B. So, like,
Okay.
I do, so I'm not like, it is definitely possible to do this with just one table instead of 2. It is, yeah, but you need to encode both of those choices in your like recurrence is what we're saying. So yeah, the last one was kind of limited in that we were saying, oh, on the last step we used B, right? But as long as you encode all of your possible choices in your recurrence, I'm pretty sure it's possible. Yeah. Yeah.
Oh, you literally mean in the second idea which machine was run like last, not just like.
Yeah,
Okay,
at time. Yeah.
Gotcha.
Question?
So by that logic, could you do this with the second idea, but containing like an extra Boolean parameter and either true or false will correspond to like having like an either A or B last?
So your table is just 2 by n instead of 1 by n. Yeah, it's the same thing, right? Yeah. Yeah. No. That wouldn't guarantee any, like, we're going to assume that all of our values are positive. And so running no machine at time I doesn't help, right?
Wait, but then how come I thought in the previous example there was like a case where they chose to run nothing.
Sorry, you're not necessarily choosing to run nothing at time I. You're saying that like there's a delay time of 1 minute, right? And that delay time then means like during that minute I get no profit, right?
No, but what I like in the previous slide, I thought there was like an underscore. Isn't it like a dash?
Right. Yeah. This means because we're switching from A to B, right?
No, but then you're adding 0. Not like this says gives 10 plus 0.
Yeah.
Because you're no longer doing anything on minute 2. You're waiting.
Right. But like I'm not going to choose to not run a machine, right? I will not run a machine if I'm forced to because I'm switching from A to B. But there's no benefit for me just like already being on a machine and then not choosing to run anything, right?
Oh, like busted.
Yeah. Right, so we get some base cases out of these two tables. Opt of A0 and opt of B0 are both just going to be 0. And then opt of A1 and opt of B1 are just going to be the value of that first job that you're running, right? Also, we're just going to make the observation that we're not going to like start off on a switch, right? Like that wouldn't make any sense for us to start with a null value on time 1. We could then initiate a switch if we want to, but yeah. Yeah, back. Yeah, right? So to get the max value from 1 to I, assuming that we end on machine A, we basically take the value that we get from running machine I or machine A at minute I, and we add it to the max of either continuing to run A at I-1 or having jumped from B at I-2, right? So we have to go 2 minutes back if I'm going to run machine A at time I. Similarly, for the second one, it's the exact same thing, just swapped. If I'm running A, then I need to go 2 minutes back, but if I'm running B, I'm going 1 minute back. It's a little confusing, isn't it? Right. So there's a lot of problems of this nature where we have like some kind of switching mechanism and some like delay that we have to wait while doing some switch, in which case like it's important to know what the optimal solutions are ending at each local decision we can make, and then we compare both of those. So then like, what's the overall thing that I want to return at the end of this algorithm? Of what? Or I guess, yeah, it's the value, but how do I get it? Yeah, exactly, right? So what we're going to return is not like opt of n or opt an, right? We're going to return the max of opt an and opt bn. Does that make sense? Is anyone confused about the recurrences? How we got there? Yeah, and yeah, like I said, this isn't like strictly the only way to do it. I did not work through a solution that doesn't use 2 separate tables, but I'm pretty sure that one exists. But either way, it would still like add another dimension, right? So like, yeah, yeah, you can either have a 2 by n table or 2 n length tables, right? So how are we going to actually build up the subproblems? Well, we're just going to set the base cases, opt of 0, opt of 1, like we defined earlier, and then just iterate from 2 to n, computing it using the recurrence that we calculated. We're slightly short on time, so I think I'm going to skip through some of the backtracing stuff, but it's the same thing that you guys have seen in class a bunch of times. Yeah, this will be posted, so you guys can read the proof afterwards. And the runtime is linear, because after we set up the tables that we need, we just need to iterate once. Okay, so here's an alternate solution, right? If thinking about opt tables made your head hurt, you don't really need to think about opt tables, right? So what if we can use an algorithm that we've already proven in class instead of trying to design our own algorithm? That'd be very nice. And it turns out that for DP problems, and if you've gone to my OpStars, you've heard me like talk about this a lot, right? Because I really like this. It's really cool. Bellman-Ford is a great choice for reductions for dynamic programming problems. Like it works very cleanly, and it makes it so that you don't really need to reason much about how opt is constructed. You just need to reason about the constraints that your problem has. And so we can reduce this problem to Bellman-Ford. And in order to do that, we need some kind of graph, right? So the idea is that at every minute, my machine can be running on either machine A or machine B, or neither machine. So I'm going to make a node at every minute for each machine. So I'm going to have nodes A1 through AN, nodes B1 through BN. And then I'm going to draw edges between 2 jobs if I can take those two jobs as like a path, right? So I can draw an edge from A1 to A2 because I can take A1 and A2, or I can draw an edge from A1 to B3 because I can't take B2 from A1, right? And the value of the edge, or the cost of the edge, right? The objective here is to maximize our total value, but Bellman-Ford gives us a minimum cost path. So how could we account for that? Yeah? Make everything negative, right? It's a trick we use in homework 2 for the MST problem as well. And then I'm going to introduce an arbitrary start and ending point just so that I have a path to compute. So what this ends up looking like is this, where I take the schedule or the input that I was given, and I construct a graph by introducing this arbitrary source and arbitrary sink. And basically the cost of each edge is the minimum of the value that I get from going to this job, right? So if I take B1, I get a cost of -5. If I take A1, I get a cost of -10, right? And my claim is that the shortest path through this graph, or the minimum cost path through this graph, is going to be the optimal solution to my problem, right? And the nice thing here is that, it does take some reasoning as to how to draw this graph. Like I was able to go from A1 to B3 and A2 to B4. But once I've drawn this graph, I can just say run Bellman-Ford and get an optimal solution. I don't need to do much more work than that. In the runtime, I just cite Bellman-Ford and have the optimal solution. The backtracking, I just cite Bellman-Ford and I have the optimal solution, right? This is awesome. This is much less work for me, at least, than thinking about the dynamic programming from scratch. So if this makes you queasy, if this makes you uncomfortable, you don't have to use this strategy, but it is very, very useful and very nice. It's a perfectly valid way to solve problems. Yeah.
So is there like a certain type of DP problem that like not like intuitively like is very applicable, like changing it to Bellman-Ford?
So maximal values on schedules are pretty solid choices. Anything where we have like some like set of things we need to pick from a larger set of things to give us a maximal or minimal value. So like the problem on homework, is it 3, 4? The one where you had to place charging stations. Was that homework 4? Yeah, that one had a very nice reduction to Bellman-Ford as well, because we could either take a charging station or don't take the charging station, and you just draw paths through all of the possible sequence of charging stations that you can pick, right? So when you can draw a path denoting a sequence of choices, that's a good way to do Bellman-Ford. And in fact, again, if you've like gone on YouTube and watched some explanations of DP problems, you've seen DP solutions enumerated as like paths through graphs, or sorry, paths through trees, right? Where have you ever seen like your DP problem broken up many, many, many times, and you take like the best path through that tree, like you do like a DFS or something like that, right? It's a very similar concept. It's just on a graph, and we take the best path through the graph. So does that kind of answer your question? Yeah. Yeah. So on an exam, you can be like relatively brief in the proof of this. To formally prove a reduction takes a little bit of work, and I would encourage you to go ahead and read the solution from homework 4, because it does have the Bellman-Ford reduction as well as the full proof laid out for you. But on exam, when you're in a more limited time crunch, if you do need to prove the correctness of this algorithm, you can kind of just assume a one-to-one correspondence and then prove why that would imply an optimal solution. So I actually have an example of the proof of correctness here, right? So the claim is that the shortest path on the graph represents a maximum value schedule on the machine scheduling problem. And we observe that there's a one-to-one correspondence between machine schedules and ST paths, right? So any path from S to T must correspond to a valid machine schedule of like choices of A or B at the ith minute, right? And therefore finding the maximal cost machine schedule is going to be the same as finding the minimal path through our graph. And since BF Bellman-Ford does return that exact path, then it must be the case that we found the best machine schedule. Right? That's kind of the idea. So I think it's quite useful. Makes a lot of your analysis easier, but again, if you don't want to use it, you are happy and encouraged to also use your standard DP techniques. Speaking of Bellman-Ford, it's a good algorithm to know. You should know how to run this on an exam. Again, time is looking a little brief, so for brevity, I think I will skip the exact explanation of this algorithm, but Bellman-Ford is the last major algorithm that you've covered in the course so far. So you should basically be able to look at the table that represents optiv IV and know what it means, and to be able to extract best paths from that table, and to be able to actually run this algorithm and fill that table from scratch. Does that make sense? Okay. Oh, and then secondarily, the assumption for Bellman-Ford is that there's no negative cost cycles. You can also use Bellman-Ford to find a negative cost cycle if one exists. And so I think there was a problem like that in your practice prelim. So yeah. It's also in the textbook, yeah. So you should definitely review that. Okay, the final topic that we have covered so far in the class, divide and conquer with a little bit of randomization. So is everyone feeling good? Ready to go on to the last one? We're almost done. All right. So we covered 3 main algorithms this semester so far. Integer multiplication, which took your elementary school n-squared algorithm and brought it down to a whopping n to the 1.6. Amazing performance increase, right? And then we also looked at quick select and median finding, which are randomized algorithms that make use of just kind of arbitrarily picking some elements. And then we looked at closest pair of points in a plane, which is maybe a little bit more complicated. All right, so here's a general approach, right? Given 2 or more smaller pieces of the problem, how can I merge all of the solutions to those problems together to get an overall solution to the problem that I'm looking at? Sorry. So we always need to have a base case, because any recursive algorithm must have a base case. And the classic example of divide and conquer is merge sort, where we basically take our arrays, split it in half, split it in half, split it in half, split it in half until we have one element, and then we just combine them in the correct order, right? And so the proof is usually inductive on the size of our input to the problem, or you can also induct on like the level of recursion, if that makes sense. Now, the type of problem that I'm describing here is like one very commonly used approach to solve divide and conquer problems, and it's one very common class of divide and conquer problems per se. But there's a second type of problem that you've seen so far in the course that doesn't necessarily do like this merge business, right? That's kind of like your binary search like algorithms, right? Where basically I recur on a smaller subset of the input to try and find some local solution or some maximal global solution to the problem, and just throw away the rest of the input at each iteration, right? So this is not fundamentally like the same thing as what we described originally. It still falls into the class of divide and conquer because I take some constant number away each time until I find the solution I'm looking for. But the proof for this is not always necessarily then going to be inductive, right? Like I don't need to assume the solutions to both subproblems are correct in order to make some assumption about the next problem that I'm choosing. I just want to show that I'm always converging to a solution that I want. And you can do that in a variety of different ways. Sometimes it's inductive, sometimes it's not. But just to be aware that there are multiple classes of divide and conquer problems that we've seen so far. Okay, so runtimes, right? Solving recurrences. We are going to go through a couple recurrences towards the end of the slides. But first thing is that you should definitely watch Jenny's video. It's on Ed, and it is a great explanation of how to solve recurrences. And typically, we have some function of the form q times t times n over p, t of n over p plus O of n. And so we can use the master theorem, which basically says relating q and p to each other, what is the overall runtime of the recurrence that we get? And rather than actually thinking about it and solving the recurrence, you can just plug it into the master theorem. What I will say is don't rely too heavily on this theorem unless you want to memorize the generalized version of this that is plus O of n to the c, right? You do not want to basically memorize this, and then if you get a problem that says plus O of n squared or plus O of 1, you're absolutely shit out of luck, right? You want to be able to solve recurrences of both types, right? Where you have a linear merge time or you have a nonlinear merge time. We've seen a lot of problems with linear merge times, but there's also problems with nonlinear merge times. So yeah. But the master theorem still works here, doesn't it? The generalized version, yeah. Okay, so just some review, right? Thinking about integer multiplication, we can split it up into these different distinct components of the numbers that we're looking at, and then we get a total runtime of 4 times t n over 2 plus O of n, which is useless because it's the exact same thing that we've already seen, right? So we don't necessarily want that. Then we observe that we can get a better algorithm by combining some of the terms and doing some subtractions. We do some fancy polynomial arithmetic, and we can bring it down to log 3/2 n. How exciting. Randomization is a topic that kind of confuses a lot of people because we're making arbitrary choices and then kind of bounding those arbitrary choices. So our algorithm basically said, I'm going to choose an element x from my array uniformly at random. I'm going to let s plus be all the elements greater than x and s minus be all the elements less than x. And I'm going to check, okay, is the element that I have the kth biggest one? If it is, then we're good. Otherwise, I need to recur on the correct direction to continue finding the kth largest element or the kth smallest element in the array. And we said the running time is O of n in expectation because we basically said the worst case is O of n squared, where every time we pick an element, it's just the worst possible pivot element that we could possibly choose, and therefore we still need to do linear work n times, which is O of n squared. But if we're able to precisely bound how much we're able to cut down our subproblem by a constant factor of n, if we're able to bring it down to 3/4 n or 2/3 n, then we bound our runtime much more effectively and get down to O of n in expectation. The reason I'm not showing the while loop with the 3/4 thing is because the book makes a claim that most splitters are good splitters, right? Like it is unlikely that you'll choose a bad splitter, and so you can still argue that it's O of n in expectation without doing the while loop thing where you continue checking until you get one in the right interval. But you should most definitely recognize how to analyze the algorithm that was presented in class, where you keep checking until you find a pivot that's within a quarter n to 3/4 n, or a third n to 2/3 n, or even a tighter bound where you would have to analyze the probabilities and runtimes accordingly. And so just some brief probability that you've encountered in the class so far. Remember that a geometric random variable models the number of trials until success. So if I have a coin and I want to keep going until I find the first heads, that's a geometric random variable. And the expectation of geometric random variables are 1 over the probability of success. So let's say with a coin, again, the probability of me getting a heads is a half. So 1 over a half is just 2. And we bound the runtime of our algorithms by using the expectation of geometric random variables. So you should be able to then precisely define a random variable over some decision that we're making over the randomness of our algorithm, basically enumerate its distribution, calculate its expectation, and use that in your runtime, kind of like you did in homework question 3 this past week. All right. So let's see. I might pull this up. How do I pull this up? How about you guys start working on these on your own, and then I will figure out how to get the solution. All right, so let's go through our first recurrence, right? This one falls very nicely into the master theorem. So we know that Q is equal to 2 and P is equal to 3/2, right? We observe that Q is larger than P, so the runtime is just going to be O of n to the log 3/2 2. That's it. Plug right into the master theorem. And that's fine, right? If you have committed this theorem to memory and you know exactly how to do this, then it is perfectly fine to just cite by the master theorem or by the theorem we learned in class, this is what the runtime of the algorithm is, right? Okay. This one is more interesting because the master theorem does not help us as much here, so we need to do some unrolling of the recurrence. So we observe that basically we're going to have a summation of work being done, and each subproblem is 2/3 of the original input size. So then how many levels do we have, right? How many levels of subproblems are we going to have? Is it 1 or 0 to start? Okay. You have log 3/2 levels. So basically, to get the number of levels total that you have to sum over, you just look at the size of your subproblem and do log of the inverse of that. Minus. Well, if you start at 1, then it's. Why? Okay. All right. Now, how much work do we do at each subproblem? Constant work, right? Constant amount of work. You can just call this of 1. Huh? Oh my. Okay. Okay. So really, you want to be slightly more formal about this. It's a constant amount of work, right? So it's actually just some constant c. Yeah. Yeah.
Long base 3 of what?
Of n. My bad. Of c, right? And the number of subproblems at each level is just one subproblem at each level. So this is kind of like what binary search does, right? And so this will just converge to whatever amount of c times the amount of work, c times the amount of levels, right? So this is just c log 3/2 n minus 1, just O of log 3/2 n. That makes sense? Awesome. Here's a trickier one. And we'll go through it just on the board because I don't think I gave you guys enough time to work through it. Okay. This one's a bit harder to solve, but we use the same systematic approach. So first, how many levels are we summing over? It's the same. It's still 3/2 log 3/2 n minus 1. And then how many subproblems do we have at each level? 3 to the I, right. Each level gives us 3 to the I subproblems. And the amount of work that we do at each level is right? 2/3 to the I times n, quantity squared. Then now we have to do some algebra, right? We'll get I'm just going to pull out the n squared because it's easier. Okay. I kind of sped through some of that because we have one more problem to get to. But basically, once I get here, right, I distribute the square. I can then pull that n squared term outside of the summation. Then I distribute the square to the I as well. So I have 2i, and then I distribute that to the terms. So I have 2 to the 2i, 3 to the 2i. 3 to the I, 3 to the 2i reduces this denominator to 3 to the I. 2 to the 2i is just 4 to the I, right? So then I can pull the I back out and I have 4/3 to the I, right? And this converges to something that you might just need to memorize. This converges to R to the K because 4/3 is greater than 1. I should post notes about this. But it,
Yeah, but the exercise is short.
R minus 1, right? But like all of this is dominated by this term,
And
Right.
like we only care about the big O, so instead of the constant.
right? So R is basically this ratio that we've gotten. K is the number of subproblems that we have. So then the total runtime is O of n squared R to the K, where R is equal to 4/3 and K is equal to log 3/2 n minus 1. No,
You can make it look nicer.
you can make it look nicer if you want, but this is fine.
There's like a log that says like a to the log b equals b to the log a. So you can write it all in terms of n power.
But this is perfectly fine. To say n squared R to the K is fine. Yeah. That's why I'm saying like don't memorize the master theorem that only works for linear time merge like operations, right? Like watch Jenny's video, understand how to like unroll them and solve it that way.
Would it be given like the formulas that were like used in lecture to
No formula sheets on the exam. But it's not that much. I mean, you should remember it from like high school algebra or high school pre-calculus, maybe. Yeah. Okay. I'll write them on the slides and then post the slides. So you're high school pre-calculus too, dumbass. Okay. One last algorithm, and I promise you it's not super complicated or super difficult. So I'll give you a few minutes to run through it. Basically, let's consider an algorithm to compute the minimum spanning tree on a graph, right? So it's a divide and conquer algorithm. And it splits the vertex set into two subsets of equal size. So I have like some V1 and V2, such that the disjoint union of V1 and V2 is V. And then I compute basically recursively the minimum spanning tree on those two subgraphs and combine them by taking the shortest edge that combines those two subgraphs. So more formally, the algorithm looks like this. And I want you to tell me, is it correct? If it's correct, provide a brief, it can be verbal, proof of correctness. If it's incorrect, give me a counterexample. Okay, how many people think this algorithm is correct? Raise your hand. It's fine. Be bold and proud if you think it's correct. Raise them high. 7, 8, maybe 9. Okay. How many of you think it's incorrect? All right. Cool. So can someone who thinks it's correct please provide an example, or not an example, an explanation as to why you think it's correct? Go ahead. Okay, so you think it's a reduction to prims, and therefore it's correct. Okay, sure. Can someone who thinks it's incorrect explain why they think it's incorrect? Yeah.
Because you can have a counterexample where you have one like a square and one edge is like 100 and all the other edges is like 1, 2, 3. And you cut it in the middle.
Yeah.
You have to take the long.
Yeah. So unfortunately, no, it's not correct, right? Here's a counterexample, kind of like James was describing, where if you let B be its own set and V2 be A, C, now technically we set equal size partitions, but it's an odd number, so you can guesstimate, right? And you can just make it apply to a square as well. Then AC has to take the edge of cost 2, but we see that the minimum spanning tree of this graph would actually be to take A, B, and B, C. And so this algorithm would not hold. Now, like questions like this are like perfectly valid exam questions, especially for like shorter time frames where we're not asking you to like come up with an entire divide and conquer algorithm. We're asking you to analyze one. I had a question that looked exactly like this on my prelim. I got it wrong, but it is okay. Life moves on, and just learn and think as much as you can from this course while you can. So that is the end of. Oh, we had one more. Fuck. Should we go through it? Yeah. Okay, so yeah, last one. This is a LeetCode question. Buy and sell stocks 1. There is a linear time optimal solution to this problem. We're gonna pretend it doesn't exist, and we're gonna find an n log n divide and conquer solution to this problem. And so, I'm not gonna give you guys time to think through it too much. I'm just gonna explain basically the intuition, and then you can look through the solutions later. Basically, I divide my set of days right into 2 subsets. And I know that the optimal solution will either be exclusively contained on one side, exclusively contained on the other side, or it will be the maximum of the right minus the minimum on the left. And so I can compare all of those in linear time by breaking this down into subproblems. So my algorithm looks kind of like this. And we do all these pointer things, I to I plus j over 2, to indicate like a subproblem of going from days I to day j. You don't have to do it like this. You could just pass in the entire array each time and save yourself some trouble. The reason we notate it kind of like this is because it saves on your space complexity. So it's just a small optimization. I would encourage you to look at this solution maybe afterwards when I post the slides sometime tonight. But yeah, like I was saying, these exams are short, 90 minutes. You really can't test all of the things that you've learned comprehensively in the course so far. Don't stress too much over it. You guys will do great. Just, yeah, keep it up and good luck.